Good morning, everyone. Welcome to Monday morning. I've got some good news and some bad news. Which news do you want first? Bad news. Your 10 o'clock lecture is cancelled. Guy Wilkinson has the longest commute in the history of... in history, he comes from Geneva, and his flight was cancelled because of a bit of wind last night. The good news is my football team, Sheffield United, are staying up this season. 39 points. There's no way we're going to be relegated now. Okay, I'll get on with the lecture. Are there any other Sheffield United supporters in the audience? Really? Yeah? I've been supporting them since I was about 7. Anyway, it's about 20 years ago. So this is the 10th lecture. We're halfway through. And I'm going to follow on from the last lecture where I talked about the energy stored in capacitors. So I'm going to follow on from that. I'm going to calculate the force between two capacitor plates, just assuming a simple capacitor arrangement, some just parallel plates. And then I'm going to go on to energy density of the electric field, give an example, and then I'm going to come on to magnetism. And there's quite a lot in this lecture, so I don't know how far I'm going to get with it, but I'll see anyway. Good. So, just to remind you again, I calculated the last lecture the work done, the energy stored in a capacitor, the energy provided by a battery, and the work done to pull the capacitor plates apart. So it's just essentially a simple capacitor, plus Q minus Q, and I want to calculate the force between these plates. And they're oppositely charged, plus Q and minus Q. This force, of course, is attractive because you've got plus charge, plus Q minus Q, and hence you've got a force between the plates. And as I said in the last lecture, by pulling the plates apart, we perform work on the capacitor battery system. Now, it's not just pulling the capacitor apart, the plates apart, the battery also does work in providing charge to the plates. Okay, and so I will just follow this through, right? So the work done in pulling apart the plates and I'm going to put a minus sign there, f dx. So I think that the minus sign is the convention in mechanics as well. So if you have a minus sign there, it's the work you put in to pull the plates apart. So so if you pull these plates apart, you're doing work against the force which is holding them together. And the energy stored in the capacitor this is, I did this in the last lecture, UC is equal to half Q squared over C. I mean, this just comes from half CV squared, and Q is CV. Right, so that's an expression for the energy stored in the capacitor. And I hope you remember this from last time. The energy stored in the battery is half that. Okay, so it's half this value. So it's equal, I'll call it UB, is equal to V times Q. Right. And, okay, so you can substitute for, so this would be CV squared, just from that. So those are the terms, and we can write down the conservation of energy. All right, and so if we change the energy in the battery, and we change the energy in the capacitor, and we do work, then the total change must be 0. Okay, so these represent changes. Right, now I'm going to do two cases, separate cases. The first case is I'm going to pull apart the plates at constant charge. So this means I charge the capacitor up and I disconnect the battery, so the battery can do no work because it's disconnected. So case one. Okay, pull capacitor, plates apart at constant charge. So the battery is disconnected. So DUB, there's no change in the battery energy, because it's disconnected. Right. So what I'm going to calculate is the force between the plates. Right, and the force between the plates is given by minus the change of energy in the capacitor as a function, so it's duc by dx at q is constant. Right, so that's just the relation between energy and force. F is du by dx. Right. It's just the inverse of u is integral f dx. Right. The work done. Right. So this equals, so the from up there, UC is half Q squared over C, we're changing the capacitance at constant charge. So this is minus half Q squared d by dx of 1 over C. Okay, from the expression up there. And so for a parallel plate capacitor, I hope you remember this formula. Capacitance. 1 over C is equal to x over epsilon naught A. This is probably the one you remember. C equals epsilon naught A over x. That's from before. I think I derived that several weeks ago, a couple of weeks ago. And I'd certainly quoted it last week. So this is the expression for 1 over C, so I can just differentiate that with respect to x. Hence, the force between the plates is equal to minus a half Q squared over epsilon naught A, so that the x just differentiates out. Right, so it's a function of only of the charge. Right, so the force, that's the force between the plates, independent of x. So what is I know it's a bit of a circular argument, this. I mean, that there is the force, so I can now get back to the mechanical work required to move the plates from separation. To separate the plates. So, of course, to do that, I use the expression work is integral f dx. Separate the plates from position d1 to d2. So that's the separation. So it's just going from d1 to d2. So I'm just moving the plates from from d1 to d2. So the work done is just the minus the integral d1 to d2 f dot dx, which equals, there's the expression for x, there's the expression for f, half q squared epsilon naught a d2 minus d1. So that's the work you need to do to separate the plates at constant charge. Right. So to recap, you can charge the plates with a battery, you isolate the battery, remove it, you've got charge between them, and that's the work done if you try to separate the plates. Right, now, the second example is the work done and the force if the battery remains connected. Right. Oh dear. So this is the case 2. Case 2, you pull the plates apart at constant voltage. Which means the battery remains connected. And now we've actually got to consider not only the change of stored energy in the capacitor, we've also got to take into account the change of energy in the battery. And remember, these have opposite signs. Right, so if you change the capacitance, you increase the energy, say, that's stored within the capacitor itself, but then you supply charge from the battery, hence reducing the energy stored in the battery. So I'm going to just use exactly the same method. So the force between the plates is the change of the total energy at constant V. So that's the expression for the force between the plates. And in this case, this is d by dx half CV squared, which is the capacitor, minus CV squared, which is the battery. So that's the energy stored in the capacitor. This is the energy stored in the battery. And it's of opposite sign to that. Right, so what we have to do is to get the force between the plates, we have to differentiate with respect to x. Right, and we're at constant V. We're at constant voltage. Therefore, the force is half V squared dc by dx, where again, c is epsilon naught A over x. So we differentiate this to get F equals minus half V squared, right, which is, I have two terms here. So I've got minus CV squared minus a half CV squared. The minus sign cancels with that. So I'm just differentiating that with respect to x. And I get left with epsilon naught A over x squared. Right, so I'm just putting all this stuff together. I have an x here which I differentiate to get an x squared, and I pick up a minus sign, and in the end I got a plus from that, and I pick up another minus sign to give that. So that is the force. So it looks different from that. All right, so the forces at constant charge and constant voltage are different. And the force here is proportional to 1 over x squared. And, right, so that means the closer the distance the plates are, the greater the force, which is sort of understandable. Right. So now there's the force. So again, it's a slightly circular argument, but I can get the mechanical work from this. Work required to separate plates from D1 to D2 And again, the work required is minus d1 d2 f dx. And there's the force. All I have to do is integrate it. So it's half v squared. We're at constant v, epsilon naught a, 1 over d1 minus 1 over d2. So I've just integrated that with respect to x, and stuck in the limits. Good. And this, of course, is half v squared c1 minus c2, which is probably the result that you would have imagined in the first place. It's just the difference in energy in the capacitor. Okay. However, you'd have got the sign wrong because of this, because of the term of the battery energy, which you should really take into account. Right, so pulling the plates apart leaves the capacitance lowered. The charge returns to the battery. Work is performed on the battery capacitor system. Oh, so when you actually pull those plates apart, although it's the difference in the capacitor, the energy stored in the capacitor, exactly twice as much work is done to put the charge back into the battery when you pull the plates apart, which is, okay, interesting maybe. Now, energy density. So that's the work done to pull the plates apart at constant voltage. My voice is gone. Oh dear. Hollow spherical shell. That's the example. Right. So, energy density. Now, in every field, electric field, there is stored energy. I mean, like the capacitor, when you charge it up, you've got the field goes from the plus to the minus plates, and that field has an intrinsic stored energy associated with it. So this is actually a general result for the energy stored in an electric field, but I'm going to use as an example the parallel plate capacitor to calculate it. Right, now, so I'm going to consider a parallel plate capacitor. And I'm going to calculate the energy stored in the field. I'm having trouble spelling that word today. So the energy stored is half CV squared. All right. And also we know the field is, here's the picture, the field is equal to V over D. So if we've got a voltage V between the plates, this is distance D, this is area A, then the field here, E, is just V divided by D, and we know the capacitance is equal to epsilon naught A over D, which I calculated the other day. So, hence, putting all this together, the energy stored in the capacitor can be written in terms of the field, which is half epsilon naught. I'm using this here, sticking in for the capacitance. A over D, E squared times d squared. All right, so I'm substituting for V and substituting for C. And that cancels with that. And I get left with UC is half epsilon naught E squared A, where A times D, where this is just the volume. Right. So that's the volume within the plates. Okay. So I can then write down the energy density between the plates. Which I'm going to call U is, I'll call it U rho for, is UC divided by unit volume. Right, and this equals half epsilon naught E squared. Right, now this is actually a general result. The energy density is given by half epsilon naught E squared for any field configuration. Right? Now, I haven't derived this rigorously, I know, but I hope you can see that this has to be the case. This is actually a general result. I'll just write this down. So it's a general result for any region of space. In an E field. Right. And this is because the volume can be made arbitrarily small. I hope that's clear. I mean, I've calculated something where in this situation the field is constant. It's a parallel plate capacitor. But I can make this volume arbitrarily small, and then I can, if then the field changes, all right, within that volume, you know, within a bigger volume, then what I can do is just integrate all the small volume elements over the whole volume. So this would be, right, half epsilon naught E squared times dV. That's the volume. All right. So that would be the energy stored within a volume element. All right, but then I can sum up all these volume elements to give the total energy density. Is then U is equal to half epsilon naught integral over the volume E squared dV. Right, so that is the general expression for energy density in any in any field configuration. So this would be over all space. In the general case. Good. And yeah, so if you need to calculate the energy of any configuration due to a field within a volume, that would be the formula that you would use. And I'm going to give an example of a hollow sphere. Now, we've done the hollow sphere before. We've got charge Q on it. All right, so here is radius R to some point out here. It's got radius A is the hollow sphere. So this is a hollow sphere. And I'm going to calculate the energy associated with this, the field of this hollow sphere. Now, I calculated the field several lectures ago, and I hope you can remember this. E equals naught for naught greater than or equal to R greater than A. So that's inside the sphere. And I hope you remember from Gauss's law that if you have charge Q on the surface of the sphere, due to Gauss's law, there's no charge enclosed in the middle, so the field is 0. Right. And if you come outside the sphere, E is equal to Q over 4 pi epsilon naught R squared for A less than or equal to R. And this is just radial as a point charge. All right. So that's the field. It goes like a point charge if you for radii bigger than the radius of the sphere, and 0 in the middle. So if I want to calculate the energy density associated with this field, then I have to do U, the energy density, or rather the energy associated with the field, is half epsilon naught. It's just the same formula over there. I'm integrating over all space from naught, over the volume, E squared dV over all space. So I've got to do this integral, and we have to use, of course, spherical polars. Just to remind you, sorry to keep harping on about this, but I think it's, we've got an element of volume here, R, done this so many times now. This is R sine theta. So, your element of volume here this is dV, and that's R sine theta. This is R theta here, R d theta, I should say. That's d phi, etc. Right? So I can write this energy stored half epsilon naught, and I'm integrating from naught to 2 pi in phi, naught to pi in theta, A to infinity in R, and I've got E squared, which is Q squared over 16 pi squared epsilon naught R to the 4th. All right, so I've just taken this field, squared it, and then I've got this element of volume, R squared dr, sine theta, oh dear, sine theta d theta d phi. Sorry about that, I ran out of board space. but you get the picture. Yeah? Pardon?
It should be epsilon naught square.
Sorry, I didn't understand.
It's here in the integral, it should be epsilon naught square.
Epsilon naught squared. Thank you. Yes, that was a mistake. Thank you. Right. And so this is the volume element, that little volume element, and I'm summing up over all space where the field is non-zero. Good. So the r squared goes with r to the fourth there, and I can take out this term out of the integral to leave me with half epsilon naught. The epsilon naught is from that 4 pi, and the 4 pi is from the the 4 pi is from the d phi sine theta d theta integral, and then I've left with this term q squared over 16 pi squared epsilon naught squared integral from a to infinity 1 over r squared dr. Right, so as I say, I'm just left with 1 over r squared. The angular integrals are trivial. That's just integral over d omega, the element of solid angle. And I've just left with the radial integral, which of course gives me, so if I do that, I just get a 1 over r term, and I get left with, I'll write down the answer, u is q squared over 8 pi epsilon naught 1 over a. All right, so that is the energy stored in this electric field. I hope you see that cancels with that, and then one of the pi's cancels, and I'm left with 1 over 8. Right. Good. And I don't even think I cheated you on a minus sign there. No, I didn't. Good. So this is the energy stored in the electric field. Now, this is really cool because I can do this a different way. Yeah, is everything all right? I don't think I've made a mistake. Are you happy with it? Yeah. So I could have used an alternative approach here, and I could have calculated the work done, it's actually written there, to bring up this charge dq. So if I've got a voltage V on the hollow sphere, then the work done to bring up charge, a small amount of charge dq, is equal to V dq, which I can then integrate up. So an equivalent expression for the calculating, or an equivalent way for calculating the energy stored, is to evaluate that integral there. Now, this is cool because if you create from 0 that charge onto that sphere, by summing up all the work, all the energy you have to put in, the work you have to do to create the charge, of course, is equal to the energy stored in the electric field when you've got all the charge in there. So all that energy goes into the electric field that you've created. And if I calculate this, we know what the the potential on a sphere is, it's just q primed over 4 pi epsilon naught a dq primed. Right? So that is the integral, which, hey presto, is q squared over 8 pi epsilon naught a, which is the same as that. Right, so we've done it via this different method by integrating the field and by integrating half epsilon naught e squared over the volume of the field and shown that it is equal to the work done bringing up the charge in the first place. Right, so that's pretty neat, I think. Good. Right. Now, does the principle of superposition apply to energy density? And this is something, it's a common mistake many students make. I'm sure I've made the same mistake before. If you have fields, the principle of superposition doesn't work. If you have two fields, E1 and E2, you can't, to get the energy density due to the two fields, you can't just sum up U1 and U2. The principle of superposition doesn't work. And just to show you this, we know the principle of superposition works for fields, right? So if you have two fields, E1 and E2, then we know that the total field is just the sum of those two fields. That's the principle of superposition. So if we calculate the energy density associated with this new field, we have half epsilon naught integral over the volume E squared dV. Right? So that is the energy associated with the field. Right. And if I now separate E squared, this equals E1 plus E2. Now I think you can see why the principle of superposition doesn't work for the energy density, because of course we have three terms here. We have half epsilon naught, the energy associated with E1 squared over the volume, plus a similar term for E2 squared dV over the volume, plus this annoying cross term, which is epsilon naught over the volume E1 dot E2. Right. So therefore, I think you can see that this one is U1 plus U2 plus epsilon naught U1 dot E2. So you can see the principle of superposition doesn't hold. It doesn't apply to energy density. So you have to, if you have two fields making up a resultant E field, then the energy density has this extra term. Okay. You can't just add up the energy densities of E1 with E2. You have to consider this cross term. Good. Good. So now it seems a bit strange coming on to magnetism. That's all I'm going to do. Well, I will do stuff in passing on electrostatics, but I'm now going to change topic a little bit and talk about magnetism, magnetostatics in particular. So this is the third problem set here. It's actually, so this problem set covers this lecture and the next one, basically. And I'm going to go through the origins of magnetism. You all know about, right, the force is BIL. That's sort of empirical-ish, which I'm going to cover the force between two, between the force on a wire carrying a current I in a magnetic field. I'll cover that. I'll then come on to the Biot-Savart law, which I don't know whether you've seen at A level or not, but this is the basically the fundamental empirical formula which gives you the force in terms of a current, an element of current, you can calculate the magnetic field using the Biot-Savart law due to that current. We now know, of course, that all the laws of electromagnetism are related by Gauss's law, by Maxwell's equations. And the only really fundamental empirical law is actually the force between two charges goes 1 over r squared. And strangely enough, everything else follows from that. I think I mentioned it in the first lecture. I can't, this course isn't advanced enough to cover it, but the laws of magnetism are related to the laws of electrostatics via special relativity, actually. So all these, everything is linked together, which is really neat. If you when you get to it, it's wonderful. So I'm then going to consider magnetic dipoles, Ampere's law, current density, and the continuity equation. Now, I think I did this in the first lecture, just to, in the early days of the early Greeks, the Greeks noticed that certain materials, iron and the like, can exhibit permanent magnetic dipoles, and they can exhibit forces on magnetic materials. Like iron magnets can become permanently magnetized and will cause, say, iron filings to arrange themselves into patterns. That was known by the ancient Greeks. It's also known, this is slightly later, much later, forces exist between pairs of current-carrying wires, and that an electric current through a wire creates a magnetic field, just like a permanent magnet would create a magnetic field. You can do the same thing with currents, and of course, in wires, and of course it's the same principle, right? A permanent magnet has internal current loops, which causes the field, just like a current through a wire creates a field. It's due to the motion of the charge. Right. And also, the magnetic field lines form closed loops. There's no such thing that we know of magnetic monopoles. Like there are certainly electric monopoles, which is just a single electric charge where the charge radiates out. For the magnetism, we always have a dipole, i.e. the magnetic field lines. They originate. They always form closed loops. Right. And just to talk about the terminology, when I say B field, I usually mean the magnetic flux density, B, The units of B, you'll be familiar with, are a Tesla. Okay, so B, the units of B, is equivalent to the T, which is a Tesla. There's the magnetic field strength is H, which is just related to the magnetic flux density by 1 over mu naught, where mu naught is this strange constant here in SI units, 4 pi times 10 to the minus 7. Magnetic field strength is in ampere meters per meter, and the magnetic permeability, mu naught, is newtons over amps squared. Right. So those you'll be aware of mu naught. I'm sure you're aware of B and H, but they're just related very simply by the constant mu naught. And okay, I think whilst of course I could go on for the next hour, I think I'll spare you that. And I'm sure if you want to stay here, you're welcome. No one else is here. You can go on Google or whatever you want to do. In the meantime, you've got some problem sets here. Okay, thank you. And if, just to say, if in the unlikely event Professor Wilkinson doesn't make it tomorrow, I will do a double lecture tomorrow. So you are going to get a 9 o'clock lecture tomorrow, you'll be pleased to hear. And if he doesn't make it, I will just do 2 lectures. He will then take over my Wednesday slot, all being well.